Yeah, good morning everybody and welcome to the next lecture in Bioprocess Engineering. Yeah, we're still talking about energy balances and you have talked in last Wednesday together with Weil about the lab course, so I assume that there were no questions with respect to the lab course, and if there are questions, please address these questions directly to Weil. But we will start now with energy balances, and of course, we will have a look at the homework.
All examples in this section are based on the Bioprocess Engineering Principles, second edition, Academic Press from Pauline Duran. The solution path is also depicted in this book, so please refer to this book for details, and it's again a warm recommendation to have a look in this book.
Just as a reminder, we had this downstream process of gluconic acid, and the final, we had a cooling with chilled water, and we had a broth of gluconic acid and water, obviously. And we wanted to calculate what is the heat loss to the surrounding. And last time we have already started, and we have assembled the flow sheet. So here we have the feed stream, we have the product stream, and we had a cooling which goes to the cooling water, a heat which goes to the cooling water, and a heat loss to the surrounding. So that was the basics of this exercise, and then we started by doing the calculation. Of course, we had to start with a mass balance, setting up the correct mass balance. That's the first thing you do always. If you do an energy balance, the mass balance here is obviously M in, M out, because there are no components involved in the reaction. It's wise to collect the extra data you need. So you see that you will need to calculate the specific enthalpies for the water. You can use the table, of course, and we also had a value for the heat capacity of gluconic acid. And it was said that you should use in this exercise, you should use, I think kilograms, hours, and yeah, kilojoule as a reference. So the heat capacity of gluconic acid was set as 0.3.5 calories per gram per degree Celsius. We have converted in the first step, we have converted the heat capacity of gluconic acid from calories per gram into kilojoules per kilogram. And it's important to do that really step by step. Here you see we have then the conversion of the calories, we have the conversion of the joules into kilojoules, and we have the conversion of the grams into kilograms. If you do it like this, then you make no error. So the major part of errors I see always in exams or whatsoever come from conversion errors. And therefore it's important to stick to this type of conversion, because that avoids you to have too many problems. Now this is your energy balance. We have already talked about that. This is the general scheme in a steady state, so it's 0. And this is translating this energy balance now into our situation. So we have a water stream which goes in, we have a gluconic acid stream which goes in, we have a water stream which goes out, we have a gluconic acid stream which goes out, and then we have no shaft work. Yeah, shaft work is not there, so we don't need it. And we have two heat streams now. We have a heat stream which is the loss stream to the surrounding, and we have a heat stream which goes to the water. And now we need to calculate everything. The water which goes in has a temperature of 19 degrees, and the water which goes out has a temperature of 6 degrees. The same is true for gluconic acid. So for water, we need specific heats at 90 degrees, at 6 degrees, at 2 degrees for our chilling water, and our 50 degrees for our cooling water. Yeah. So this is just something we look up. So we go to the steam table, which was here. Yeah, it was the steam table. So we can directly look it up. We have here 2 degrees, and we take the specific enthalpy. We have 6 degrees specific enthalpy, 50 degrees specific enthalpy, 90 degrees specific enthalpy. There is no latent heat here. It's we are all in liquid water here, so we can take that. So these values you simply then put in the formula, so that's very simple. This is something we don't do now together because we have already shown how this works. You just multiply it with the mass and that's it. Now for gluconic acid we don't have these values, and then but we have the heat capacity. So what we do is we set the reference stage as 90 degrees because this is what we can do as we want. So we just set it at 90 degrees, the reference stage, because we only need the relative one, so that's 0. So we don't just need to calculate then the difference to 6 degrees. That's it. And this we can do then straightforward. The formula is of course this H gluconic acid out is equal to the mass for this heat capacity T2 minus T1. And I have of course now forgotten what number the formula has, but and this is 400 kilograms fold 1.47 kilojoule per kilogram degrees Celsius. So this is what we have converted. This is this value, yeah, and fold, and now we have the difference of the temperatures. The T2 is the 6 degrees Celsius minus 90 degrees Celsius. So this is small. 90 degrees Celsius. Okay, so here we are. Maybe I make it a bit bigger that you have a chance to read it. 6 degrees Celsius minus 90 degrees Celsius. And if you put everything in your pocket calculator, you should get 4.03 times 10 to the 4 kilojoule. So therefore, we have now this value. This value is 0. So we have calculated this value. This is 0. These values come from the steam table. So we directly multiply then with the mass, the value of the steam table. And now we need to know what is going into the cooling water. So that's the next thing. So the Q loss is of course the one we want to calculate. So the cooling water stuff we need to calculate next. And this is also simple. So just put away the mess that it doesn't look so messy here. We set the heat removed by the cooling water is the water between 2 and 50 degrees. It's exchanged with 2,700 kilograms per hour water, which was initially at 2 degrees, and it goes out at 50 degrees. So what we need to calculate is simply what heat is in this water. So this is in principle what we do is the same. We do an energy balance now for the water. However, we just have an input and output stream. There is no shaft work, and calculate the heat. So we just put it in, and this is a very simple calculation for the water. M cooling water in minus M cooling water out is equal to Q. Yeah, so this comes from the energy balance. You had the energy balance minus Q minus plus WS is equal to 0. This is gone, and then this is directly the Q of our cooling water. So we have directly then is equal to Q. And we just calculated. So Q, again from the steam tables, it's 2,700 kilograms. And we then take the specific enthalpy at 50 degrees, 209 kilojoules per kilogram minus 8.4, that is 2 degrees kilojoules per kilogram. So you can look it up at your tables, is equal to 5.2 times 10 to the 5 kilojoules per kilogram. And this is the Q water. Yeah. So this we put in our, again in our balance. And then we have everything. We have the specific enthalpies of water from the steam tables. We have calculated the specific enthalpy for gluconic acid out. We have calculated the amount of heat which has been transferred to water. Then we pack everything in the formula, and then we end up Q is equal to 7.01 times 10 to the 4 kilojoule per kilogram. No, kilojoule, it's over. Sorry, not per kilogram, kilojoule. And this is also, sorry, my error was here. Here, this is if you are at the board, even if you're sitting in front of your board, you make errors. Of course, this kilogram here drops out, so it's not kilojoule per kilogram, it's kilojoule, and therefore here we end up with kilojoule, otherwise it makes no sense. Okay, so that's what we get out simply by putting everything inside. You see that the calculation here was very straightforward. We used always the specific enthalpies, or we used heat capacities, and that was it. Yeah? So it was not more than that. So the difficulty was more or less that we had to put in all these different we have to assemble all these different values. So it was not really the difficulty of the calculation, because it was just multiplying 2 for 3 at the end. It was not really complicated. This Q was positive. It was 7.7 times 10 to the 4 kilojoule per kilogram. As we have defined at the very beginning that our heat flow goes out, and therefore we have already assigned a minus to it. If we get out a positive Q, this is important for you to know, this means that heat is being removed. This means that in our equation, due to our definition, with a positive Q means that it is being removed. If our Q is at the end negative, that means that we need to heat up the system in our energy balance equations. That's important that you keep that into your mind. But maybe I will have a look first at the questions. Yeah, so wouldn't it be negative? It's for mass balance of gluconic acid. I'm just switching. Oh, yeah, that's wrong. Thank you very much. Sorry. So this has to be negative. So because it's 6 minus 90 degrees, it's negative. Sorry, negative. Thanks for this hint. At that point, we always talked about energy balances without a reaction. So of course, for us, the most interesting thing is not this cooling stuff downstream or whatsoever. This is at the end physics or thermodynamics. We are interested in when a reaction happens, and of course, we're interested in a biological reaction. That's what we are all talking about, and that's what we are interested about. So let's see how this looks like. So the heat of reaction, this is something you already know from thermodynamics. So of course, you know how to calculate the heat of reaction. So you see the heat of reaction is equal to the sum of the specific enthalpies of the products minus the sum of the specific enthalpies of the reactants. And of course, in this you have the temperature and so on inside the specific enthalpies, but you have also this internal energy inside, so how energy rich your substance is, and you can simply do this calculation. And at the end, if you are below 0, you have an exothermic reaction, so energy is being released, and if you're above 0, you have an endothermic reaction. So this is what you have learned in chemistry, so this is nothing new. Now, to calculate the standard heat of reactions at 25 degrees and 1 atmosphere, what you can do is, usually you don't have these values, so the heat of reactions as the specific enthalpies are usually not listed for reactions. What is usually listed is for each compound the standard heat of combustion. So these heats are the heats which are produced. You can directly see that if you burn the substance completely, how much heat is being produced, and this is the standard heat of combustion. And of course you can use then these values, because you remember enthalpy is a state function. You can use these values to calculate the heat of reaction, and that's very simple. And so your delta H at 25 degrees 1 atmosphere is then simply the sum of the standard heat of combustion of your reactants minus the sum of the standard heat of combustion of your products. That's it. And then you have your delta HRXN. Okay. So now, if you want to calculate that, a heat of reaction of an enzymatic process, your question could be, well, what is the standard heat of reaction of the enzymatic transformation of malic acid into fumaric acid? So that's, again, what you have more or less learned in chemistry. This is not something which is new to you. So we have here malic acid, we have fumaric acid, and we have the standard heats of combustion. We have for malic acid minus 1328 something kilojoules per mole, and fumaric acid minus 1334 kilojoule per mole. And you have seen before, of course, you can do always these equations either with mass or molar values. It depends on what you have, what has been listed. Yeah. And the reaction equation is this one. So we have here the sum formula. So of course, you know that this is a reaction you have already seen in biochemistry. So reaction equation, and you produce water. What is the standard heat of combustion of water? You might think of that. As long as I ask the question, I give the response in a second. Of course, 0. Water is fully oxidized H2, so there is no way to burn it anymore. This is the end product if you burn something with hydrogen. Yeah, so that's 0. So that's that. In other words, you don't need it for water. Of course, the same is true for carbon dioxide. It's 0. So you don't have a heat of reaction for carbon dioxide. Okay. So you have one, but it's 0. So this means you can simply put that in your equation. So you use simply your equation here, the standard heat of reactions of your combustion of your reactants minus the standard heat of combustion of your products. So this is something I will not write on the board to save to avoid the risk of again that my system breaks down. So you can directly calculate that. And then you come up with a solution, and you have the delta HRXN is 1 mole malic acid minus 1 mole fumaric acid, and we come up to 5.2 kilojoule per mole. So in other words, this reaction is an endothermic reaction, and therefore you bring heat into the reaction. This is then if you are at the standard conditions, but often your reaction is of course not at standard conditions. So usually you work at 37 degrees and so on. So you, of course, if you have listed your standard heat of reactions, what are you doing? Well, you remember enthalpy is a state function. So the cool thing is, what you do is, as always, you start with your reactants at for example 30 degrees, you cool down to 25 degrees, there you use then your standard heat of reaction, you're at 25 degrees, and then you heat up, or in this case it's water and your fumaric acid, you heat it up again to 30 degrees, and that's it, and then you have the difference. So this is how you can do that with your standard heat of reactions. Now, this was an enzymatic reaction, so this was not growth. Yeah. So if you look at these values, so you see that our heat of combustion was 1,300 something. Yeah. Our standard heat of our reaction was just 5.2 kilojoules per mole. Honestly, this is a very low exothermic endothermic reaction. This is a kind of a reversible reaction even, because the delta H is so low. So delta G is of course then the one which we need to know with respect to reversibility, but nevertheless this is kind of a reversible reaction. So there is not much heat being produced here. We use these huge standard heats of combustion to calculate the small heat of reaction here. So you see it's only 0.4%. So therefore, if these values are not precise, these are also not precise. So in enzymatic reactions, it's kind of problematic if you use, let's say, imprecise standard heats of combustion to calculate this. These values will be kind of vague. This is especially true for these enzymatic reactions. We usually said that sensible heat changes are not an issue, but in this case, sensible heat changes are in the same range. So if we need to heat up and cool down something, we will talk about that later on again. If we look at our reactions where we have our biomass growing, sensible heat changes are in the range of 1 to 10 kilojoules per mole for reactions at 37 degrees. So in this case, we have to take into account these sensible heat changes. Nevertheless, if you estimate cooling or heating requirements for these enzyme reactors, usually the first calculations can be quite error prone because your precision of your values might not be enough. So it's better. The error also you will see later on for our calculations with the heat of reaction in case of biomass is also there. However, we are in another dimension, so therefore we can feel more comfortable with these calculations than with calculations in enzyme reactors. However, we will not talk too much about enzyme reactors. You talk about enzyme reaction engineering in a separate lecture. This is just something I want you to be reminded at that point, that for enzyme reactors, sensible heat changes are of importance. That's what I wanted to say. The difference between 38 and 39, I think both questions go to the same direction. 39 and 38, the standard heat of combustion is already a reaction. So this is what the difference is. It's integrating two things into the primary formula, where you have this sum of the heat of reactions. I'm just going back to the slide. The enthalpies, the absolute enthalpies, and here you have enthalpy differences. And of course, this comes from this equation. However, you come from heat of combustions, which are reactions, and therefore this then turns the sign, and therefore it turns the equation. You can try it yourself, yeah. Don't take it too complex. If you have heats of combustion, just use this equation, and if you come with enthalpies, you can use the other one. Okay, so we said this was an enzymatic reaction, but what we're interested in is, of course, something where we produce biomass. So we want to assess heat of reactions associated with cell growth, and the question is now, how can we do that? So we have the standard heat of combustion, of course, for all our substances, but what is the standard heat of combustion for biomass? One thing is you can measure that, of course, you just burn it and measure it. But another thing is that there is a correlation, and that's cool, that helps us. So, and there is an empiric observation that the energy content of organic compounds is directly related to the degree of reduction. Most organic substances follow this equation. So you see that if we plot the degree of reduction over the standard heat of combustion, you see that we get a straight line, and we have lined up all our compounds. We have lined up there. Why? Because, of course, the higher your degree of reduction is, the more you can burn it, because the more electrons you have to be transferred to oxygen. At the end, combustion means electron transfer to oxygen, and the higher degree of reduction is, the more electrons you have to be transferred, the more energy is being released. And this, as I already said, is the methane or so has the highest energy content, because it's the most reduced form, and you can, by the way, you can calculate now the degree of reduction of methane. Please put it in the chat. What is the degree of reduction of methane? And then you will see, this is the highest amount of electrons I have to transfer. Therefore, more energy needs to be released. And if you then just measure these energies for different substances with different degree of reduction, you come up with this straight line, and you come up with a simple equation that you your standard heat of combustion is equal to minus 115 kilojoules per mole for the degree of reductions for the number of carbon atoms in the molecular formula. So remember, the degree of reduction is the available electrons divided by the number of carbons. So you need to bring back, of course, then the number of carbons in this case. So this is very cool, because then you can, even if you don't have the values listed, you can come up with the heat of combustion for any substance. Yeah? Of course, it's not absolutely exact, and for an enzymatic reaction this might not be an ideal way, but for our what we are talking about, if we talk about growth, then this is fine to come up with these estimations. What is then the standard heat of combustion for biomass? So if we use now this average biomass formula and we assume that we have 5% ash, then we can come up with the following standard heat of combustion. So we say the formula, so we just take this formula here. So I have my 100 minus 115 kilojoules per mole fold the degree of reduction. Of course, that is what we calculate out of that, 4.8 fold 1, because it's 1 carbon. And then we convert it to masses here with our biomass 25.9 grams per mole, and then we end up with a heat of combustion of biomass using this formula, using the average formula of minus 21.3 kilojoule per gram. So per gram is of course for biomass more relevant than per mole, because what is a mole biomass? This is just a let's say a kind of helping us to bring that in the formula. But of course, again, some formula of biomass with respect to chemical composition makes no really it has no relation to chemistry. We can of course also measure it. It of course depends on the molecular composition and growth condition. And this will change, of course, then also this one. So this is an average formula. So if you go for experimental values of bacteria and yeast, you're here. So bacteria has a heat of combustion around about of minus 23.2 kilojoules per gram, yeast of minus 21.2 kilojoule per grams. And you see, we are quite exactly in this range. So this already is not too bad. Yeah. So this means that we can, this calculated value we could use, of course, if the value is listed, we can also use the listed value. Yeah. Okay. What I said before is, I said at the end, heat of combustion means that I transfer my electrons to oxygen. So in other words, if I have I forgot to look whether some of you have now came up with a degree of reduction of methane. 8. Yes, the degree of reduction of methane is 8, and you remember in this table, this is on the rightmost part of your table. So this is the most reduced organic substance, is methane. Yeah. So 8. So at the end, this equation is nothing else than transfer of electrons to oxygen, because this is combustion, transfer of electrons to oxygen. In other words, you would say in the case of methane, you transfer 8 electrons. The degree of reduction is 8 in the case of methane. You have 1 carbon, it's methane. So you transfer 8 electrons to oxygen. Yeah. So in other words, if you look at this equation, this means that our heat of combustion of methane is simply this term here, fold the degree of reduction, in other words, fold the number of electrons we have transferred, and this is 8. So in other words, we can say, we can on the one hand look how many electrons do we have to transfer, but the point is, in our aerobic metabolism, if we have a microorganism growing aerobically, then it means, well, the heat of reaction at the end is nothing else than how many electrons are being accepted by this oxygen which goes in. Because this is at the end the net oxidation which is happening. The other electrons are just transferred. But at the end, it depends on what's going into oxygen. Only these electrons are lost in oxidation. So if I have no other oxidizing agent or so in my reaction. So this is cool. In other words, I can also look at just how many oxygen did I bring in this equation, because this is of course directly correlated to how many electrons are transferred to the oxygen. So I don't need to look at the other components. If I'm interested in the heat of reactions in an aerobic reaction, I just can look in how much oxygen has been consumed, and that's it. And as I know that per molecule, per element of oxygen, I have 2 electrons which I can transfer. The available electrons, remember, for oxygen is -2. So each atom of oxygen I bring in will take 2 electrons, and this means then it's twofold this -115, but each molecule of oxygen has 2 oxygen, so I have 4 electrons which are transferred per mole oxygen which I bring in. 4 mole electrons. Yeah. So one O2 molecule which I bring in my reaction will capture 4 electrons. So in other words, it corresponds then to the degree of reduction of 4, which is then taken over. And I can directly use that. So what I need to do in this case is I can then calculate the heat of reaction simply by I use this 100 minus 115 kilojoule per mole and multiply it by 4 per mole of oxygen. And then I have it. So, and this is very cool. So this is one of the most important equations for you here, and it's a very simple one. So for fully aerobic metabolism, what happens? Dog comes in, but he's laying down, going to sleep. So I'm just closing the door. This is what I need to train with my dog, that he knows how to close the door. This is not yet perfect. Okay, hopefully that now the stream is now better than my dog with respect to closing the door. So again, coming back, in the fully aerobic metabolism, it's enough just to look in aerobic metabolism how much oxygen has been consumed, and just using this oxygen amount, I can calculate the heat of reaction. And this is this very, very simple formula. The delta Rxn for the fully aerobic metabolism is nothing else than minus 400 kilojoules per mole fold the oxygen consumed. Full stop. And this is regardless of whether I have growth with and without product formation. So this helps me a lot because I don't need to calculate or sum up the heat of combustion for all of my reactants and so on. I can simply put this one. And even more, if I have a reaction which is not yet balanced, so if I need to know the heat of reaction of a reaction where I don't have yet the balance for all of the reactants or products which appear in this reaction, I don't need to do it. As soon as I know how much oxygen has been produced, I'm fine. And this is very, 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 very important. I have to look at the watch, otherwise I would have added some more varies. Yeah, because in the exam, especially when you have a lack of time and when you have an aerobic metabolism, in general, if you want to come up with a heat of reaction, of course you use the amount of oxygen which has been consumed in your reaction, because that's way faster. And if in the exam it's simply asked how much oxygen has been consumed, what is the heat of reaction, just do that. So then we go on. So this is just experimentally this has been assessed, and so that's fine. That really works. And now if we have an electron acceptor, of course in a reaction not necessarily always oxygen is our electron acceptor. It could be also something else, and then of course it doesn't apply. So then we need to calculate the heat of reaction based on the heats of combustion. So we need our the formula we did before. We do the same as we did for our enzymatic reaction. We need to sum up then the heats of combustion, and then we just use the simple formula and calculate the standard heat of reaction. Then we just put that in this formula. So we have the substrate here plus the ammonia minus biomass minus product. So these are the standard heats of combustion, and then we have at the end the standard heat of reaction. So we put it in this formula 39. Again, I recommend you always have the formulary next to you in order to look it up. Now, if we now look in our cell culture. Now we have, you remember, we have, if we want to do an energy balance, we have the heat of reaction, yes, but what we also have is, we just talked about heat of reaction now, but you remember we have streams which go in our reaction, we have heats, we have stirrers, we sparge, and so on. So there are many things which are involved with respect to energy. And of course remember, it's an engineering approach here. So we only want to use things for our calculations which make sense. So in other words, which are relevant at the end. So if it's just 10 digits after the comma, the difference, this is cool for mathematicians, but it has no impact at all with respect to the design of the cooling system or value whatsoever. So we will omit that. We don't want to make our life more complicated as necessary. So the question is, if we use this equation for the steady state process, input stream, output streams, we want to know what are the factors which are relevant for enthalpy differences with respect to input and output stream. Now, let's have a look at a typical contribution for aerobic fermentations. And so we have, of course, the reaction itself. So the growth on carbohydrates, this is the heat of reaction. We are in the range of 5 to 20 kilojoules per second per meter cube. So this is quite high. So if it takes longer, you produce more and more energy and you don't ferment seconds. Yeah. Growth on hydrocarbons, we are in the range of 60 kilojoules per second per meter cube. So of course on hydrocarbons, you have a higher degree of reduction, and therefore you produce way more energy. So this is the heat coming from the reaction. Now, what comes from the shaft work? So if we are in large vessels, we are in the range of 0.5 to 5 kilojoules per second per meter cube. In small vessels, we are in the range of 10 to 20 kilojoules per second per meter cube. So we can put on more energy in small vessels. So you see that in small vessels, the energy coming from the shaft work is in the same range as the heat of reaction. But in larger vessels, the energy of reaction exceeds that. Now, what comes from our latent heat? So remember, we evaporate, especially in aerobic processes. We will evaporate water, and here we are in the range of 0.5 kilojoules per second per meter cube. This is not this is lower than our metabolic reaction, but depending, of course, on the time, this can be relevant. So especially in this metabolic reaction, if I look at a culture where I start with a low biomass concentration, of course, the heat of reaction will be also low if I come with a small biomass concentration. The evaporation is a phase change we have in a sparged culture. And there, if we sparge, we will have a relevant input, or in this case, decrease of heat from our system. And latent heat is at least in the same order of magnitude than our heat of reaction. What I didn't look at, because I switched now to the next slide in order to make the stream more smooth, is the sensible heat. I quickly go back. So the sensible heat is what I put in. For example, my liquid stream goes in with 25 degrees and my reaction is at my bioreactor is at 30 degrees, or it's warmer or whatsoever. So therefore I have a sensible heat change in this case. However, this is really order of magnitude smaller. The same is true for heat of mixing. If I come with a concentrated glucose solution in a fed batch reactor, this is orders of magnitude smaller. So the sensible heat is in general not relevant. So usually you don't look at sensible heat changes in the case of bioprocesses. Remember, that's why I had this for the enzymatic reactions. So if you have enzymatic reactions which are not highly exogenic or endogenic, then these things can be different. But for growth in a bioreactor, in general, sensible heat changes can be neglected. So this is cool, because if we know that, we can modify our steady state energy balance equation for cell culture, because then we don't look at this coming in, coming out things anymore. We neglect every temperature difference of things we pump in or pump out. We just look at the heat of reaction. That's of course something we cannot neglect. And we look at the heat of vaporization in an aerobic process. So there, this is relevant. We need to put it. And of course, we have again our heat leaving the system and our shaft work. So in a steady state, this is now our new energy balance if there is a reaction. And that's of course very simple, because we then can say, okay, we just need to calculate our heat of reaction. Remember, if it's aerobic, it's very simple. If we know that there is that it's sparse, we need to know how much water is lost due to evaporation, and then we can calculate based on that the latent heat of vaporization. And of course, we need to know what is the energy input by our shaft work, and then we can calculate how much energy is being produced in the system. In other words, how much heat must be removed by cooling. So that's a very straightforward then approach coming to a modified energy balance. In this energy balance, remember, we have neglected sensible heats. There is no extra term for the heat that if we have an incoming stream where we have a lower temperature or higher temperature, we neglect that. So you remember that what you have calculated in your exercise example 8, this was, of course, only sensible heat changes what you did there, because in this case, of course, you had a cooling process. Of course, there it's relevant. But in a real bioprocess, these sensible heat changes don't play a role, because, of course, you don't put tons in per second cold water and take it out. You have your reaction going, and the streams you put in and out, even if it's a continuous fermentation process, are very small in relation to the volume of your liquid, and the streams in and out, the heat difference is usually low. So you come in with a 20 degree and go to 30 degree. That's a very low heat difference. So that's of course different if you look to chemical reactions. Yeah, so that's also important, or enzymatic reactions. Now we come to the next example, which is citric acid. And believe it or not, this is your next homework. This is citric acid production. This is a very, I would say, this is a very important homework. Yeah. So this is something really take care that you can solve it. Remember what we have talked about. Aerobic, anaerobic processes. So remember, we are all talking about now this equation, which is our modified steady-state energy balance equation for cell culture. This is the equation in general to be used. We neglect sensible heats, and if there is nothing else written here, then we can neglect it. Now you see in this example, 2,500 kilograms glucose has been consumed to produce 1,500 kilograms citric acid and 500 kilograms biomass and other products. Use ammonia as the nitrogen source. Power in the system is inputted by agitation is about 15 kilowatts. 100 kilograms of water is evaporated. So you have all information here to be put into this equation. So you want to know the standard heat of reaction. You want to know the latent heat. You have the amount of water which is vaporized. So this is relevant. Of course, you want to know the cooling requirements, and you have a stirrer work. So you have everything, and this is then the thing you need to calculate. And you see 860 kilogram oxygen. So in other words, it's an aerobic process. So assemble, we are again at this assemble part, and you say this is now not fair because this is your question, and we skip it a bit because we would have done that. We will have a look on the flow sheet, but you should assemble at home. All information, assemble just means bring everything together what you want to know. So and all information in addition you need. You want to know also the mass balance, which is applicable, but you need to think of whether you need it or not, or whether it's sufficient to use the oxygen, because the question at the end is you want to know the cooling requirements. Yeah? Now, flow sheet, of course, you have to draw a system boundary. Yeah, I think I will have to remove that because it is always asked the system boundary, but it's not really an issue. And then you calculate and finalize. 1 point. So this is the flow sheet. Also, again, please try that yourself. Yeah, try that yourself. So I have my streams. I have 2,500 kilograms glucose going in. I have ammonia going in. I don't know how much. I have my bioreactor. I have 1,500 kilograms citric acid going out, 500 kilograms biomass going out. I have 860 kilograms oxygen going in, and I have 100 kilogram water vapor going out. Obviously, also carbon dioxide and so on goes out, but this is not even given here, so I didn't put that stream here. But this off gas usually you would have, so that's would be better to have this here. But okay, so you also have water in this stream, you also have water in this stream, but again, it's a energy balance at the end, so we neglect the water as it's cut it out anyhow. Then we have a stirrer work which goes in, and we have the energy we need to take out with respect to our cooling requirements. So this is your flow sheet. This is what you use, and using that you want to calculate. Oops, am I with the right note? Yeah. The question how much heat is being removed. So that's the homework for next week. And now let's have a look whether there are more questions. What the answer on the question example? Why do we not include the water in the feature? Okay. So I'm still the answer on the water with respect to the feed stream. I think this is I asked you, and there was not yet the response. Okay, so here we have not the reaction water. Why is it not in this process, although it should be in the mass balance? So obviously, for the energy balance, if we neglect the sensible heat, neglecting sensible heat means that the water which goes in and the water which goes out is not accounted for, because even if it brings in at 25 degrees and goes out at 30 degrees, we said that we neglect the sensible heat. So we don't need the water which goes in and out. We only need the things which are in the reaction to calculate the heat of reaction, because remember, we want to take this equation here, and you see that there are no streams anymore with the internal energy. So you remember the first energy balance we have set up. There, it's the sum of masses going in fold the specific enthalpies minus the things which go out, the sum of the things which go out minus the specific enthalpy. So there is, of course, also therefore with this equation it was possible to calculate what we did before with this cooler. We had different temperatures, we had no change in the components, there was no reaction, but there we could calculate cooling requirements or the heat loss to the surrounding due to sensible heat changes. In this equation, there are no sensible heat changes anymore. We have dissected this equation. We have simplified this equation just to things which are relevant in a system where we have a reaction. And therefore, we just have a reaction. And there, of course, the in and out streams of the reactants and products are internalized, because you can calculate the heat of reaction based on your products and your educts based on the heats of combustion, of course, but there you have the streams. Here we need to know what is being evaporated and of course the shaft work, and just this is now being considered in this flow sheet. I have no shaft work, so it's not there. I have a feed stream, I have a product stream, and no evaporation in this case. Yeah, if there is evaporation, I will also have this water which is lost due to evaporation. So you see that there is no complete mass balance set up in this, because I don't need it. So what I would say now at this point is thank you very much for your attention. Sorry for the problems at the beginning. So that's the reason why I will put this example 9 calculation then in a separate part. I think the other calculation should be clear because we did it then. So thanks again for your attention. Looking forward to seeing you next week again, and have a nice weekend.